Welcome back to our afternoon section. There is a list, you must assign it. It will pass for you assigning. Okay. This talk, I guess I will finish in 8 minutes, okay? 1 hour or 3 and 20 minutes, right? Okay. So I left you some exercise. I don't know if you already done, but I hope you tried, okay? This is the last one. And now I will talk about quantum algorithms, and I will start talking about quantum oracles, because there are different kind of algorithms. One of these is the oracular quantum algorithms, and this is the first kind of algorithm I will talk about. So it's important to introduce you the idea of an oracle. Okay. Quantum oracles, similarly to classical oracles, let me see here, okay, is a black box. A black box in the sense that we don't know the working process of this box, okay? Suppose that we want to evaluate some function, and you give to me this function. I will do the process, and I will return the result for you. But you don't know how I did this process, okay? That's the basic idea of a black box. So when you are solving black box oracular quantum algorithms, the idea is just to know how many carries it's necessary to solve the problem, okay? We carry the oracle, and the oracle returns the answer to the problem. So what is an oracle? Oracle is basically a Boolean function. Boolean function is a kind of function whose image is bits. Okay, the image is composed by bits. Suppose here n bits, and the result is n bits and m bits here. This could be any function of n to m bits, right? This is an example. This symbol here, these diagonal lines crossing the qubit line, means that you have n qubits here. So the x state is a state that describes n qubits, and y is a state that describes that is described by m qubits, right? And this is a controlled operation in which n bits are now controlling these m bits. And the resulting operation is that one. You remember that this is the XOR operation. For this reason, we call this kind of oracle XOR oracle, right? So here X is the input state, and Y is the target state. What's the goal of this kind of computation? Observe that f is a function of n, so our goal is to know f, right? For instance, if you take y in the 0 state, 0 cross 0, 0, 0, and so on, tensor product of many qubits in the state 0, then we obtain that the solution here is just f of x. More precisely, this operation, the XOR, when you're dealing with more than one qubit, this XOR operation is performed qubit by qubit, right? Qubit 1, qubit 2, and so on. And in this case, suppose that the Y state originally is the tensor product of m qubits. It's clear this kind of notation for you, right? For those that don't know, this kind of notation means n times, right? So we are talking about m qubits in the state 0. But it's possible to transform this kind of oracle, the XOR oracle, in a phase oracle. We'll show some examples here using the phase oracle, but as you can see, they are equivalent. In this case, suppose that originally our state y is in the minus state. Do you remember the minus state? Plus minus 0 divided by square root of 2, so x 0. And if you apply the x gate, we flip this qubit in the 0 state to qubit 1, and then you apply the Hadamard gate, we get the original, the input state, x tensor product with minus state. If this is the initial state, let's follow a bit of calculation here, okay? This is the original state. I distribute the tensor product here. And when apply the oracle, we observe that it will be necessary to perform this XOR operation here and here. Observe that oracle is a linear function, as the unitary operations in quantum mechanics. And then it's necessary to evaluate these two situations. Suppose that f of x is 0. Then we find 0 XOR 0 is 0, and 1 XOR 0 is 1. And in the other case, is if f of x is 1, we get 0 XOR 1 is 1, and 1 XOR 1 is 0. Observe that these states are similar, except by a minus sign here, okay? So it's possible to conclude that if the function f is 0, then minus 1 to the f of x will return a positive sign here. Otherwise, it will return a negative sign here in the case of f of x is equal 1, right? In this way, it was possible to transform this XOR oracle to a phase oracle. That's the basic idea of the action of the oracle phase oracle, right? It depends on the power of the function, okay? It's clear? So, carry complexity. Carry complexity means the number of calls to a function, how many times we consult the black box, okay? And depending on the problem, it's necessary sometimes, for instance, as in the Grover search algorithm, to consult square root of any. In this case, n is the dimension of the Hilbert space. However, in the classical case, you just you need a greater number of carry to the oracle that's linear with the Hilbert space. Okay? In this case, observe that there are a different number of carries. So we call this kind of separation as oracle separation. And this is basically the speed up in this kind of problem. The number of times you call the oracle, right? So our task here is to apply these ideas in a simple example. Probably you already heard about Deutsch algorithm, Deutsch-Schosse, and Grover algorithm. Yet or not? Okay. If not, please just ask. The problem is the following. Let f of x be a Boolean function, domain 0 and 1, and image 0 and 1. This function is promised to be constant if the function is constant, it means that f of x is equal f of 1, independently on the value of the function. It could be 0 equals 0, 1 equal 1, right? Or balanced if the value of the functions f of 0 and f of 1 are non-equal. Okay, the problem here is to determine if the function is balanced or constant. Just that. In general, what you need to do if you use a classical computer? It's necessary to know the value of the function, or f of x and f of 1, and compare these results. And if they are equal, the function is constant, otherwise it is balanced. Okay? So it's necessary to bit, at least 2 bits of information to encode this information that's the result of f of 0 and f of 1, right? The idea here is that it's possible to create a quantum algorithm that just carry once, okay? And this is based on superposition or quantum interference. The original problem proposed by David Deutsch, David Deutsch found a solution to this problem, but his solution was probabilistic. There was, again, in fact, about over classical computing, but this is the best solution to this problem, right? This is a new version of the solution. So the problem is the same, right? But now we have a quantum circuit that is able to solve this problem with just one carry. The algorithm is the following. Initially, the qubits start in the state 0. Then a Hadamard gate acts on this qubit, and it goes to a superposition. Then the oracle, do you remember that the effect of the oracle on the states is that phase arc, right? -1 to the power of f, here and here. And then, again, the qubits pass through Hadamard gates. In this case, it's necessary. 0, the 0 is transformed to 0 plus 1 over square root of 2, and 1, 0 minus 1. So the final state is this one, right? So this is the final state before a measurement is performed, right? But how do you know the solution to this problem in quantum mechanics? You just need to measure. When you measure this final state, we will find 2 possible solutions, or 0 or 1. If you find the solution 0, means that, okay, this amplitude is equal 1, and this amplitude is equal 0. If this amplitude is equal 1, the only way, or plus minus 1 actually, and the probability that's 1. So if the amplitude is plus minus 1, then we'll find here that f of x must be equal to f of 1, right? It's clear? Suppose that f is a constant function, so equals 0, and then the result here is 1, 1 divided by 2 is 1. If f of 0 and f of 1 is 1, minus 2, okay, power 1 is the same number, so minus 2 over 2 is minus 1. So the amplitude of probability is plus minus 1, and the probability is 1. Consequently, as this state is normalized, this amplitude must be 0, right? So if we measure the state 0, the function is constant. If we measure the state 1, the function is balanced, right? This is possible to see here because this sign minus, then at the end of the computation, if the function is balanced, just this amplitude will be plus minus 1. Right? It's clear?
From information theory perspective, it's right to tell that the previous problem in the classical case, in comparison to this new problem in the quantum case, the information available was compressed, like you told. Before we had 2 bits of information, and now we have just 1 qubit of information. I can do that parallel, like the information compression channel oscillate. I can do that.
Okay. The question here is if there was some compression process when you compare classical solution with the quant one. Observe that I don't think so, because we are talking about a carry. You just are carrying the oracle. So I believe that the answer to this question is, in the quantum world, it's possible to carry simultaneously in parallel, and then you get the answer in an easy way. I will show in the next slide how this problem can be seen from the perspective of interference. Okay? I guess, yeah. So, yeah, it's clear the idea of the simple algorithm. This is the most simple algorithm in quantum mechanics, right? In quantum computation. Okay, here you can understand this problem as an interference problem. Okay, let's start with qubit in the state 0. After the Hadamard gate, the system splits. I mean, 2 paths, right? And then each path passes through the oracle, and each state acquires a phase depending on the value of the function, right? And then when you pass through another Hadamard gate, the system splits again. However, it's due to the finite dimension of the system, that's 2, we observe that these 2 states, this one and this one, they will sum up to this value, and these 2 states will interfere constructively, returning this solution, right? So this is an interference process. You can see this as an interference process. In the case that if the function is constant, just this part will survive, and if the function is this is balanced. Sorry, this is not constant. Okay, I will correct it after this presentation. So this is the case which survives if the function is constant, if the amplitude survives, if the function is balanced, right? Can you understand this as an interference process? Okay, right. Okay, the question now is, can we generalize this problem by considering more cubes instead just of 1, and consequently, more functions to be available? Okay. Observe now, if you have a function f whose domain takes into account n qubits, and in the image is just 0 or 1, as we have n qubits, we have 2 to the n possibilities, or 2 to the n values of this function. But there is a constraint. This function can be just or constant or balanced, right? If it's constant, all these values are all equal, meaning 0 or 1. And if this function is balanced, half of these values are 0 and half 1, right? Okay, suppose that we try to solve this problem classically. How many carries it would be necessary to decide if the function is constant or balanced? Suppose that the dimension of this space is 100. How many carries it's necessary to be sure that the function is constant or balanced? 51, right? Because if you evaluate just 50, the function can be balanced, but you don't know in the next step could change the value. So it's necessary half of the possibilities plus 1, right? In this case, we are sure that the function is balanced or constant, right? So half of this number that is exponential is also an exponential number of carries, right? This is the solution to this problem that we call a deterministic solution, because you are sure that the solution is constant or balanced. Because there are also the possibility you make a guess, okay? Maybe, maybe not. You have some chances of being right or wrong, right? I will explain this after. So there is an exponential number of carries to do the classical oracle. Let me remember you about this word separation, this oracle separation. In this case, we observe that if I have a quantum algorithm that is able to decide with just one carry, we observe that there is an exponential separation, right? This is true, right? But just when we are interested in the deterministic solution, in which case we must be sure that the function is constant or balanced with 100% sure, okay? Okay, let's show how the quantum algorithm works. This is an optimized version of this circuit. This is not the original one proposed by Dave Deutsch and Richard Josa. This is proposed by Colin, Skeen, and Houghton. Because the original version, in the original version, they use an auxiliary qubit here, but it's not necessary. In this case, all qubits are initially in the state 0, then they pass through a Hadamard gate, it cubed, right? Goes to a Hadamard gate. And then they pass through the oracle, the phase oracle, right? Again, they pass through Hadamard gates, and they are measured. It's quite common when you study quantum algorithm, you find this structure. Hadamard gates, a great unitary, and Hadamard gates, again. Do you think is there a particular reason for that? Let's come back to this example. Hadamard, operation, Hadamard. This results in interference. This kind of structure is the same for high-dimensional systems, right? So this is the idea of interference. When you put all the states in superposition, it's not possible to follow the path in each state will follow, right? So this is an interference process. Okay, let's follow now the algebraic of the problem. I mean, step by step, trying to understand the application of the gates of the lecture during the morning, right? The initial state is this one, is the tensor product of n qubits. Then we apply the Hadamard gates in each qubit. This is the same as the tensor product of plus states, right? In this case, you have n plus states. And now I am writing this state in this way. Can you follow this passage, these two lines? Maybe the easiest way is, let's take, for instance, two qubits. 0 plus 1, 0 plus 1. Okay, 2. It's necessary to do all these multiplications. So the final state is a combination of all possibilities, right? And now imagine this for many qubits. Okay, if you have many qubits, you'll find 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, until 1, 1, 1, 1, 1, 1. Okay? In this case, we will have 2 to the n states. Right? So, in other words, the idea of using Hadamard gates is to create the superposition among all the basis states. That's the idea when you use the Hadamard gates here, right? And these are all the possibilities. This is the binary representation, right? Or integer representation here. Sometimes we use this kind of representation or sometimes this kind of representation. Do you remember the conversion between binary to decimal representation? No? Yes? Yeah? Okay. Just, okay, suppose that you have, it will be useful in the next slides, right? This is a simple way in which you can write a given number, let's say z. Okay, this will be useful later. It's clear, and this Q0, Q1, Qk are the binary values, or 0 or 1, right? Okay, in the second step, we pass this state into the oracle, and what the oracle really does is give a phase depending on the value of x, right? -1 to the f of x. And again, we'll pass this state. This is the state before these Hadamard gates. And after, we'll pass this state in the Hadamard gates. There are different ways of performing this calculation. You can actually act with all these Hadamard gates on this state, or you can think as a measurement in a different basis. Instead of measuring in the computational basis, if I put a gate in front of the measurement, I will move the base in which I am measuring. In this case, the action of the Hadamard gate on the state 0 is plus, and the Hadamard gate on the state 1 is minus. This means that these gates and these measure apparatus are measured in the plus-minus gates, right? That's equivalent. You can show in the exercise after, right? So what we need to do here, we need to measure in the plus-minus base this state here, just that. How can you do that? If you, instead of calculating all possible values, I will just measure, supposing that the state I am measuring is a tensor product of plus states, right? This one. So this is the state here, before that Hadamard gates, and before measuring, I am asking in a different way, what's the probability of finding this state as a tensor product of plus states? This is equivalent. We already saw that a tensor product of plus states is the same as a linear combination of all element bases, right? So when you perform this product here, observe that X describes basis element, Y the same. So the product here is, the inner product here is the delta between X and Y. If they are equal, okay? Okay, delta is 1. If they are different, delta is 0. But the final answer is that this one. Observe that what I am saying is, suppose that the function is constant. So I am performing the sum of -1 if f is equal 1. So I am performing the sum of -1, 2 to the n times here. Or if f of x is equal to 0, I am performing the sum of 1, 2 to the n times. So the final result, if the function is constant, is plus or minus 1. What does this mean? Observe that the probability is conserved, right? If I measure this amplitude plus minus 1, it means that the probability of finding the system is 1. If I measure all the states in the plus state, this means that the function is constant, because there is no probability of finding the other possible combinations of the basis states. For instance, if you are measuring and you find a different result from plus, and you find plus, minus, plus, minus, plus, minus, this is not possible. If you measure, is this equal 1, so the function must necessarily be constant. Okay? In other words, if you return to the original basis, you can think that if you measure all the qubits in the plus state, it's equivalent in the computational base states, that is 0 and 1, to find the system in the 0 state, right? This is equivalent. You just need to return, okay? So this is the idea. By measuring just once, okay, it cubed, of course, we'll find that the function is constant or balanced. In other words, if you measure all the qubits in a state plus, the function is constant. Any other possible combination, the function is balanced. That's the case. If the function is balanced, observe that half of these values will be 1, and half of these values will be minus 1. So when you sum all these values, the result is 0, right? So if the function is balanced, it's not possible to find the system in a tensor product of any plus states. It's clear, or a bit confused? Right? Okay. So in this case, observe that you are getting the answer with just one oracle carry. So in this case, we say that there is an exponential speedup.
In the case of a constant function, if I understood right, that means I can find a product state from the output, right?
You find, oh, okay.
I can find a tensor product state from the output. This is it.
No.
If
No.
If the function is constant.
Okay. Let me try to explain again. Sorry. Here. Okay. Until now, this is the state of the system, right? Before the Hadamard gates. Okay, what I tried to do here was to simplify your life, just that, but probably I confused a bit more. But what's the idea here? The idea is the following. Suppose that instead of measuring the computational basis, you measure in a rotated basis. This basis is the plus minus base, right? Okay. And suppose that if you measure all the qubits in the plus state, if you measure all the qubits in the plus state, observe that what we will find. You find that the function is constant. Because if the function is constant, this means that this sum over 2 to the n is equal plus minus 1. if it is plus minus 1, this means that all this state exactly the tensor product of plus states, right? So if this probability is 1 by conservation of probability, it's not possible the system to be found in any other configuration that is plus, minus, and so on, right? That's the key idea. So the idea was, instead of I apply the Hadamard gates and measuring the computational base, and after doing a post-processing, I decide, okay, let's just look to the rotated base. That, at least to me, it seems simple. So the final message, yes, if you measure this state, and it is exactly in the plus state, the function is constant. Otherwise, any other combination that you measure, plus, minus, the function is balanced. In this way, just need to measure at the end and observe the result. If the result is plus, function is constant. If the result is any other different of this, the function is balanced. So with just one carry, we find the solution to this problem. So we got an exponential speedup. It's clear or not?
Now, I confront myself because of the zero tensor state. Shouldn't be a plus here, down there, in the conclusion.
Okay.
Or the result of measure.
Okay, this conclusion is because, sorry, this conclusion here is because suppose that you return to the measurement in the computational basis, it's equivalent to measure all the cubes in the state 0. That is the case, right? When you measure in this rotated base in the plus state, it's equivalent in the computational measure the system in 0 state. That's right, thank you. Okay, it's clear?
No.
Okay. Okay, so you are thinking that, okay, I found an exponential speedup in a very easy case, right? But it's not the case, sorry, okay? It's possible to find a probabilistic classical algorithm that solves the same problem with high probability, closer to 1, if you perform classical carries. The number of classical carries here is k, the number of measurements, I mean. So if you, for instance, carry classically 5 times, your probability is already very good, right? So this is an exercise that I will let you, okay? Yeah, you will have also my presentation, the slides, so there is no problem, right? But this is a simple reason that if you make the following question, what is the best deterministic way of solving this problem? That's right, there is an exponential separation. But if you admit that there is some probability involved, okay, classical and quantum computing do the same task, right? In the same efficient way. Actually, I already performed some research on this problem, and according to the algorithm I used, quantum mechanics was worse than in the classical case, right? Okay, this is the basics, the simple problems we call Deutsch and Deutsch-Joseph. And now I'm moving to other famous problem, that is the Grover search algorithm. But before, let's following this example, right? Suppose that we have this telephone book. We know that it is ordered by alphabetical order, right? As shown here. And the ask I am doing is, what is the cost or the number of steps I need to find one name in this list? Okay, this is in principle easy, right? Everyone here is able to do that in a short time. There is a classical algorithm named binary search algorithm that is able to perform this task in in a very short time in a logarithm behavior, right? How can we understand that? Suppose that you are looking for the name Charlie. What you can do? This algorithm says, okay, split this list in two parts, and we observe, okay, I am in the middle between D and E, so I must take this part of the list. Again, I split this new part of the list in two. I observe that, okay, this part of the list includes just names with A, so I need Charlie, then I move to this part of the list, and so on. Take half of the names at each step. So at the end, the number of names, if the number of names is n, and the number of steps, okay, 2 to the number of steps is equal 1, because it's the number I need to do. So I find that the number of steps in every when I invert here this expression, and I found that k is log of n, right? So this is an efficient algorithm, but the principal observation here that our list is ordered. However, it's possible to complicate this problem, just change the question. If instead looking for a name, I am looking for a given phone number. Now, the things are much harder, right? So, what's the number of carries you need to do in order to find a given number? Suppose that you want to find this number, 1, 2, 5, 6, 6, 3, 7. Okay? That's the idea behind the Grover's problem, not exactly to apply to classical database, okay, or to apply this Grover search algorithm to, for instance, to find states in a given Hilbert space in a given basis. That was the original motivation of Grover's algorithm. Okay, so it's possible to state this problem of find a given phone number in a list, in a telephone book, in a different way. Suppose that you have a Hilbert space of dimension n, and you want to find just one element of this, of the base of this Hilbert space, right? This is an equivalent problem. So you can state the problem as the following: find the only entry x0 in this string, such that this string refers to the all base states, okay, as I mentioned here. And the answer of the function is 1 if x is equal x0, the target state, the desired one, and the function is equal 0 if x is different from the target state. Okay, this is the function. I mean, this function will be performed, will be represented by our oracle, right? Okay, in general, the classical solution to this problem, we need to looking for, on average, for n names in the list, okay? But the basic idea of the Grover algorithm, it's possible to reduce to this complex to square root of n, right? This is proposed by Love Grover in 1996. Observe that this is just 2 years after the Shor's factoring algorithm. And these two algorithms, they were very important for the field of quantum computing because this kind of strategy, I mean, if you have a speedup, even polynomial speedup that is a quadratic speedup, it's important, mainly if you are working on algorithms that are heuristics, okay? Because in general, solve, for instance, NP problems, NP hard problems, it's possible to accelerate this kind of process that you use in a classical computer. But using the Grover's algorithm, but just with a speed up that square root, right? Okay, this is the circuit of the Grover's algorithm. Again, we start the qubit in the state 0. I mean, n qubits are n Hadamard gates. And after that, we apply this gate G k times. We don't know how many times yet. K we'll discover later, right? And now I introduce this operator that's called Grover's operator. This operator is composed by an oracle, Hadamard gates. This operator that we will interpret later, this is basically also some kind of oracle that gives minus sign in all the base states, but it not give the sign on the 0 state, right? Here is an abbreviated notation for 0 is equivalent here to 0, 0, 0, right? And this is and I is the identity operator for this multidimensional system. So the basic idea is just create a superposition state and then apply a given number of times this Grover operator that has inside it the oracle. That's the basic idea. Let's follow each step of the process. Most of you already know how this algorithm works or not? No? Okay. Let's start the initial state, the tensor product of qubits in the 0 state, and then we create the uniform superposition, as we already know. Remember that this uniform superposition is the uniform superposition of all the basis states, x represented here. So we have 2 to the n base states here. This is the normalization condition. And here, I guess, in here is two to the n. That's the dimension of the Hilbert space. And what we are going to do here is split this state that's a uniform superposition of all the base states. We will split it in 2 parts. One part, observe here, that is x0, that's the target state. And the other part englobes all the states less x0, right? And I multiplied by these factors, yeah, because I want to normalize this state. Observe that here we are sum to n minus 1 base states. For that reason, the norm of this state is this one, right? So now I have the combination of this state with these states. X0 is a base state, is a normalized state. This state now is also normalized. We use these 2 names. Okay, this state I will call beta, alpha, and this state I will call beta. So there is a relation between these amplitudes of probabilities multiplying these 2 states, right? Observe that initially, if you ask, what's the probability of finding the system in the state alpha, it's very close to 1, if you give that n is very large. And there is a very small probability of finding the system in the target state, right? What's the idea? When apply the Grover's operator, the idea is to amplify that amplitude, right? That's the basic idea. You see at the end of this presentation that there is another quantum algorithm called amplitude amplification that is exactly a generalization of this algorithm, right? So the Grover algorithm, then the idea is to amplify this amplitude. And we will do that by using the Grover's operator. So let's try to understand the action of the Grover's operator. Before, we will see the effect of the oracle on the base states. We already know that oracle acts on one base states. It's -1 to the f of x multiplying the state x. This is the case. If f of x is equal 1, this means that x is the target state. So in this case, if f of x is equal 1, then a minus will appear here. Otherwise, if the function is 0, this means that the x is not the target state, so the state is not marked. What I mean with this oracle is that the oracle is just marking the state, the desired state, with a sign -1, just that. Okay? So let's see the effect of the oracle on the state alpha. We observe that all the base states x here, they are in this situation because all states are different from x0, right? Or this sum exclude x0. So the effect of oracle, it's nothing. So the final state is the same. Oracle f acting on the alpha state is alpha, and the oracle act on the target state. We know that a minus sign appear here, so that's the effect. And this will be important because through this minus sign, it will be possible to perform reflections, as I will show next. Okay. Let's rewrite the Grover operator in the following way. This is the expression of the Grover operator, right? The original one. And what I'm doing here is applying these unitary Hadamard gates, right? Here on the state 0 and here on the state 0. Observe that the action of the Hadamard gates on the state 0 is that state is the tensor product of plus states that is equal our initial state, right? Or let me show you our initial state is exactly this one, the tensor product of plus states. So we have, in this case, the projector of psi state, the initial state. As the Hadamard gate is a unitary operator and squared Hadamard gate is equal identity, in this case, the result is the identity. And again, we preserve the oracle operator here, right? This is a simple way of observing the functioning of the Grover operator because it now would give to it a geometrical interpretation, right? It is clear to now? Where? Sorry.
Like in the technically before, it's in the first slide about the whole problem. In the very first part about this problem.
Okay.
Like we have one list of names, and it is crucial that it is in order, right?
Right. The name is right. Yeah.
Because like otherwise, if the other side was in order, it would be the same problem the other way around, right? If your numbers were in order, it would be a problem to ask for a name.
Yeah, exactly. Yeah.
But like I don't understand how the information is in the font conversion. Like how do you make this kind of thing precise, like mathematically?
Okay. This is encoded in the oracle. Suppose that to each name, to each number of our list, we associate one state of the base states. x0, x1, x2, and so on. There is an direct association, right? And you try to find a specific number. Suppose that corresponds to x10, right? So it's necessary to build an oracle to looking for this x10, right? That's the idea. I won't go into details how to build for specific problems, but it's possible to do. There's a lot of papers showing this application that it's possible to accelerate different algorithms by improving the search process. So what I'm saying that it's possible to do, but I don't go into the details here, at least in this presentation, how to do that. You can talk later, maybe during the exercise. But it's possible, right? Yeah, here, yes, the oracle here, it's, let me try. Okay, after I will discuss some simple example. If some of you probably already studied this problem on the IBM site, you find that is a simple example. If you have 2 qubits, you want to find the state 1, 1. It's simple to build an oracle for this specific case. You can discuss this example later. Okay. Okay. We are now here. Okay. So this is the Grover operator. Pay attention that this is the initial state. I will explain more about this operation here in the next slide. But let's see what's the effect of the oracle on our initial state. Observe that when oracle acts on this initial state, there's the uniform superposition. But when written in terms of alpha and beta, we observe that beta is the target state, so just a minus sign appears here, right? And you can interpret this in this 2-dimensional plot. In this axis, we find the target state, vertical one, and in this axis, we find the alpha. It's possible to understand this initial state psi 0 here. It's very close to alpha. Why? Because, observe here, the amplitude of the alpha state, suppose that n is very big, it's quite close to 1, right? Otherwise, the projection on the beta state is very small, right? So what's the effect? So this is the initial state. After the application of the oracle, the projection beta acquires this minus state, so there is a reflection. Observe that this is the projection along the beta state, but now it has a minus state. So this is a reflection around the alpha axis, right? Clear? And now, what is the effect of this part of the Grover's operator on the previous state? Psi1, observe that this is this state, this is this one, okay? The effect of this operator is the following. Identity operator, it doesn't change the state, but this part changed the state. I mean, there is a projection of the state psi1 on the direction of state psi. How can you understand the effect of this one? In this direction, we have the state psi, right? Originally, the state psi1 is here. Psi0, in this case, is exactly the same, the state psi, right? Psi1 is below the state psi0 here. But this projection is multiplied by 2. So this vector is exactly the projection of the state 1 along the state psi multiplied by 2. 1, 2. And then, now we make the subtraction of the state minus psi1, So the final state, geometrically, it's possible to understand that the psi2, that's the result state of this operation, is a reflection with relation to the axis described by state psi. Did you get? Or not? Okay, let's go back to our two-dimensional picture here. This is the initial state. I apply the oracle. There is a projection below the alpha axis. Then I apply this other part, and there is a reflection, with relation to this state, okay? Observe that with just one step of application of the Grover operator, the state that was initially here are over there, and the angle here is theta plus theta over 2, right? So you can convince yourself just by projecting here the state psi along the direction of alpha that cosine of theta over 2 is exactly the projection, the inner product between alpha and psi. And if you return here, the projection between alpha and psi is this number. So what we are doing here is establishing a connection between the theta, the angle, that will be very important for the next steps, with the number of states in the database, right? So it's possible to invert this operation and establish a connection between theta and n. That's right? Okay, I'll move a little bit faster, sorry. Let's interpret the Grover's operator. There is one part that is the oracle, but there is another part. We already understand that, okay, the oracle imprinted minus phases in front of the target state. And nothing doesn't have the complementary states. But what's the role played by this operator? To understand that, we decide to write the identity operator here. Observe that you are describing the system as a two-dimensional one, right? Although it's 2 to the n, you are reducing to the representation of a two-dimensional space. So the identity operator in this case is the projector of psi plus the complementary projection, okay? This means that if you substitute this expression, the identity here, in this expression, you'll find that this expression one. We can, sorry, it's repeat. Ah, yeah. Okay. What we are seeing here is that the initial state acquires a minus phase, and the other states, they remain unchanged. That's the action of this operator, right? This will be important if we're trying to generalize this to perform the amplitude amplification of other states, right? But in the particular case of the Grover algorithm, it's possible to understand that the Grover's operator is the minus times an operator that amplify or mark the initial state with minus, and other operator that's the oracle operator that gives a sign in front of the target state. So if you apply this G operator, the Grover's operator, a given number of times, observe that after one application, the state is displaced by an angle theta. And again, if you apply again, theta, 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 and so on, therefore we are asking, what's the number of times k that I need to apply to be very close to the final state, the target state beta? This is the question. In order to do that, observe that here this angle between psi 0 and alpha is theta over 2, and I am applying k times theta here. So k times theta plus theta over 2 must be pi over 2. That this is the angle between these two states. So k can be written this way. And if I use that previous expression to write theta as function of the dimension of the system, then I find that theta can be written in this way. So if I use the Taylor expansion series here of the arc sine, then I find in first order this term. I will consider just this first order, right? Because I am supposed that n is very big, so these other terms are much smaller than this one. Then I find with this value of theta and replacing this expression, here I find out that the number of carries, the number of times I apply the Grover's operator is pi over 4 times the square root of n. I mean, it's possible to be very, very close to the answer problem, right? Just carrying square root of n instead of n as in the classical case. But we can ask, what's the success probability of this algorithm? In order to do that, we know that x0 is the target state. G applied k times on the initial state is the final state. So is just to project this, and we find that is a number, and observe that this number is a value between that is greater than cosine of theta over 2. And write these terms in terms of n, we find that this probability of success, if n is large, is very close to 1. That's very important. Okay? But there is an important information that I won't talk about here, that the Grover's algorithm is also optimal. There is no way, if you are using quantum mechanics, to achieve this result in a smaller number of steps. Okay? This is important. There is no algorithm better than Grover's to search in an unstructured database, right, in quantum mechanics.
I just have a question. Theta is the angle between the initial states and the cat alpha, is like that?
Theta is the angle.
The initial angle.
This is the initial state. This is the state after the action of the oracle. So theta is.
My question is, in the expression of the number of the steps, the k, if theta is equal to pi over 2, what's the geometric interpretation of that?
If theta is
Pi over 2.
pi over 2.
I think you get 1/2.
Okay. The problem here is that, observe that if you have a large database, theta will be very small. So if we are talking about a very big theta, right? Pi over 2, this means that every time we apply the system, we will start, for instance, from here to there, to there, there, to, okay? If you think it like a clock, you are, yeah. So it's not useful.
So it's like I'm passing the pages of the list like that. So if I have a list of objects,
I don't think so, because it means that we have at most one state in the list, or two at most, right? Okay, I think it's time. Celso asked me to finish at most 3. It's okay, Celso? Yes. Okay. So thank you. If you have questions, please. No questions? Okay. Thank you for your attention.